In the previous lessons, you learned how to use a stoichiometry problem where you have to convert from mass of A all the way to mass of B, which is one of the product in your chemical reaction. But that is a very simplified type of problem because you only have one type of reactant converted to another product. But in most cases, or in most reaction, you would be given the values of all the reactant in your chemical reaction, and you have to determine which one of those reactants will be limited. That means will be used up first. We call that reactant limiting reactant. And that is basically the reactant that is going to be used up first, and it will determine how much of the product is going to be made. In this case, we are going to look at those problems, and we have something called the Rice table. Now, the Rice table is basically, we have the reaction that needs to be balanced first, followed by the initial amount in moles. And notice how it's always in moles. And then we would calculate the change in terms of x by looking at the coefficient. And then lastly, we would find how much is left at the end of the reaction by looking in terms of moles by taking the initial minus the change in terms of the coefficient. But before we look at an example problem, we need to look at this strategy right here. How do we determine which reactant is going to be limited? So to determine which reactant is limited, this is what you're going to do. Assume all reactants are limited, and we're going to solve for the x values of each of those reactants. And then the one that has the values of x, which is going to be used up first, hence the term limited, will be the limiting reactant or the limited reactant. Okay, so let's look at an example. Here I have my R, which is the reaction. And let's go back to the problem. 80 grams of copper react with 25 grams of sulfur. We don't know which one is the limiting, which one is the excess. Will produce how many moles of copper sulfide? And I give you the molar mass for each of those substance in the problem. Well, go back to the table. We have R as our reaction. Now we have that reaction already balanced. And of course the coefficient is 1. Okay. Now we're gonna go to our initial. What is the initial? It has to be in terms of mole, because mole is a universal unit that allows us to change to any unit. So in this case, for copper, what do we know about copper? Copper, we have 80 grams, okay? So to convert from grams of copper, all we have to do is divide it by the molar mass. So first we have to convert grams of copper to moles of copper. So we have 80 grams of Cu, and we're going to time that by the molar mass, which in this case, copper is 63.5 gram and equal to 1 moles on top. And we do the math. This give us 1.25 moles of copper, okay? And we're going to do the same thing to another reactant. In this case, we only have 2 reactants. So this is sulfur. We have 25 grams of sulfur. So we have 25 grams of sulfur. In this case, grams of S times by the molar mass conversion factor. In this case, the gram going on bottom. And that's 32.1 gram, 1 moles on top. The gram cancel out. And this is sulfur, of course. We have 25 divided by 32.1. And give us 0.779. So we have 0.779 moles of sulfur. And what about the product? Well, initially, at the beginning of the reaction, there isn't any of the product being formed yet because they haven't reacted yet. Now, that is the initial. This is where it's going to get tricky. It is the change. That is for C right there. Well, what do we say about C? All we have to do is look at the coefficient and put it in terms of X. Now, look at this. If this is a chemical reaction, all these 2 reactants will react with each other to make the product. So that means they're going to be used up. Therefore, we have a negative number of X. And we look at the coefficient, that tells you it is minus 2X. Where on this reactant for the sulfur, the coefficient is 1. So we are going to have minus 1x. What about over here? Of course, we are going to be adding instead of subtracting for the product because we're making product as a chemical reaction occurs. So we have plus X right there. So now this is where it's going to get tricky. Which one of the two reactant is limiting? Well, we don't know, so we had to use this strategy. We had to assume that both of them are limited. And then from there, we look at each of the X values. So how does that work? If they are limited, that means all of them going to be used up. So we take the initial, okay? We take the initial 1.25 for copper minus 2X. This is the rate that's being used 2 times compared to 1 time in terms of sulfur. So what we have here is X is equal to what? 1.25 divided by 2. So we have 1.25 divided by 2. This gives us X equal to, in this case, we have X equal to 0.625. There you go. And that's X. But what about sulfur? Let's assume sulfur is a limiting reagent. That means it's gonna use up. So we take the initial 0.779 minus 1x equal to 0. Because we use all of it. That's why we have 0 on this side as well. So now, what we have here is x is equal to 0.779. So which one is gonna be the limiting reagent? This is where it's gonna be tricky. We have to use a common sense and prove it. The limiting reagent is the one being used up first, okay? Let me assume that this is your limiting reagent. Let's make an assumption, okay? So how can we prove that this is wrong or right? Well, in this case, we can prove that it's already being using up and equal to 0, but is this really happening in this case as well? So let's check it out. So let's make a scenario. Let me change to different color. Let's make this scenario where x is equal to 0.779. So if that's the case, we have 1.25 minus, in this case, it is the consumption of minus 2x, so minus 2.779. And then we're going to solve it, okay? So in this case, 2 times 0.779 is what? 2 times 0.779 give us 1.55. So we have 1.25 minus 1.55. And that is impossible to be occurred in this reaction. That means, see right there? 1.55, that means you require more than 1.25. So therefore, it tells you have an excess amount of this substance in terms of sulfur. So therefore, this cannot be the limiting reagent. Just to explain this again, we assume that this is the limiting reagent, all right, which is x equal to 0.779. And both of them are x, okay? And we can prove that if it's not a limiting reagent, or it is, by looking at the other reaction and we plug in x. And we prove that, in this case, copper only have 1.25, but if we plug in x values as 0.779, and we have 1.55, that is a lot greater than 1.25. So we need more copper to react with that 1.55. So therefore, this cannot be the limiting reagent. But let me prove it the other way around, where let's assume that this is the limiting reagent. So here, I have my initial value, which is 0.779. Okay, that is coming from here, assuming the changes, minus 1x. So 1 minus x, but in this case, I'm using x as 0.625. And what does that tell you? We have 0.779 minus 1 minus 0.625 will give us an extra values, right? In this case, 0.779 minus 0.625 give us a leftover of 0.14 moles of, what is it? In this case, it's gonna be sulfur. So this proved to us that this has been used up first. And we have the leftover of sulfur. So therefore, this right here must be our limiting reagent or limiting reactant. And now, how about the product. Remember, we can see the change in terms of x. And if x is the one that is going to be approved as 0.625, because this is the limiting reagent, so what does plus x really mean? It's just plus 0.625. And that is how much mole of copper sulfide is being produced. It's easy, isn't it? So now, what if I want to make this problem even more challenging? If I have mole, what do you think I'm going to ask you? Well, I'm going to ask you convert mole to grams. So how many grams of sulfur is going to be left over? Well, let's solve this problem. So we have 0.154 moles of sulfur is left over, and we're going to convert this to gram. Easy. We go back and look at a molar mass, which is 32.1. So therefore, now we have 1 mole on the bottom for sulfur and 32.1 grams of sulfur on the top. So plug into a calculator, 32.1 equal to 4.94 grams of sulfur left over. Easy, isn't it? There you go. Now let's try, in this case, what if I don't want how much mole of copper sulfide is being produced? I want the amount in grams. How is that going to work? Well, the same thing. Convert this from mole to gram. Time that by the molar mass, which in this case is 159.1. So we have 1 mole on the bottom, in this case Cu2S, and 159.1 grams of Cu2S. And the mole cancel out. We have 0.625 times 159.1, and that gives us 99.44 grams of copper sulfide, and that is how much being produced by the limiting reagent of. It's easy, isn't it? Now, what if I want to increase the rigor of this problem, and I continue to ask you, what if the reaction above made 90.5 grams of copper sulfide? What is the percent use of the reaction? Well, think of percent. What is percent? Well, percent is always about 100. Well, in this case, what is U? Well, when we talk about U, that's how much we make, okay? So in this case, how much we make in the reaction. Well, what is that being compared to? Well, of course, the values being made is compared to the theoretical number. What is the theoretical number? It's 100% efficient. So that is being compared to theoretical. What does theoretical means? That means calculated. You use your mathematical application to calculate it. In this case, how much did we calculate it? Turned out to be 99.4 grams of copper sulfide. And what we're going to have here is, of course, go back, we compare it, and that's the theoretical value. So this right here is theoretical. And what do you think the top part is going to be? Of course, this is going to be the actual values. And that's what percent U is equal to. So percent U is equal to the actual values divided by the theoretical values. And we know this is calculated, right, using a stoichiometry flowchart. So let's plug this in. We actually make 90.5 grams, so 90.5. And what is theoretical values? We calculate that is 99.4 grams, so 99.44 grams. And times by 100, what is our percent use going to be? Turn out to be 91.00% U. And that is pretty good, 91% efficiency. That is super awesome, isn't it? And that is how you use the Rice table and relate to limiting reactant.